Okay, good morning. Let's continue with our discussion of chapter 3. We'll finish up the theory about capacitors and then go into the example problems. Okay. All right, so we stopped right here where I described how a capacitor, the basic operation of a capacitor, right? When you apply a voltage, there's a charge imbalance between the voltage source and the capacitor plates. And so electrons flow in the circuit and charge builds up, which we can then measure as the capacitor voltage across the two parallel plates. Let's see. Can everybody hear me online?
Yeah, we can hear you.
All right, thank you. So let's talk about discharging. If you take the capacitor of a fully charged capacitor out of the circuit, ideal capacitor, it'll hold its charge indefinitely, right? Ideal capacitors would be made of ideal materials. If it's ideal material, then the insulator that is used is also ideal, meaning it has infinite resistance. There is no pathway for the capacitor to discharge that stored energy. But in real life, that's not the case. First of all, the capacitors that we deal in real life are very, very small. So the charge that they hold is also very small. The energy that they store is also small. In a real life capacitor, the insulating material between the plates is not ideal. And hence, the capacitor actually discharges. Actually, let me draw it. And if there's charge buildup on both sides of the plate, it discharges through that insulator itself. Okay, it discharges through. Slowly but surely, all of the energy will be dissipated and lost. Okay, and so we can model a real life capacitor with a resistor in parallel. Okay, resistor in parallel. Of course, that resistance has a very high value. It's a very, very high value. So it behaves like a insulator in most case scenarios. But if you take a fully charged capacitor out of its circuit, after a certain period of time, that capacitor will lose all of its stored energy. And we can say that it loses it through that parallel resistor. So for an inductor, we model the resistance in series. For a capacitor, we model it in parallel. Yes. So the question being asked is about how long it takes. That depends on the circuit parameters, meaning the value of the resistance and the stored energy, the amount of stored energy, which we will look in chapter 4. There are videos online where you can actually see. So if you take a small charge capacitor, you take it out of the circuit and you just short the two leads together. What happens? R, the resistance is now 0 because of the short between the terminals of a capacitor, right? It's like a battery. So a charged capacitor would be like a battery. It stored energy. You short the two terminals of a battery, what happens? All of that energy is discharged to that pathway. That pathway has low resistance, short circuit, very, very close to 0 ohms. So if R is 0, I is infinity. All of that stored energy is released in an instant. In a charged capacitor, the energy stored is finite. When you short a charged capacitor lead, again, all of that energy, stored energy, is released in an instant, and the capacitor discharges. Depending on the amount of energy stored, you might see a small spark. If it's a battery, battery capacity is also finite, but it is huge compared to a small capacitor. So if you short the terminals of a battery, take any coin cell battery or 1.5 volts battery, R is 0, current is infinite, energy is being released all at once, you will see an explosion. Depending on the size of the battery, depending on how long it's being connected or short-circuited. A real-life example would be what happened a few years ago with the Samsung Galaxy Note 7. Do y'all remember? Exploding phones. If not, look it up. So in the pursuit of making phones thinner and smaller, somebody at the battery design center decided to actually make the walls that separates the cells very, very thin. So what happened was it short-circuited the battery cells inside that phone. And because it short-circuited, obviously all of that energy is being released all at once, it gets overheated. If it doesn't stop, then the energy continues to be released until all of the energy is gone, results in an explosion. And that's what happens. Anyway, so capacitors again, charge capacitor, you take it out, it'll store its charge for a certain amount of time, but it discharges slowly internally. Capacitance of a capacitor is the amount of charge that it can store for every unit of volt that is applied. Mathematically, we write it as capacitance C is equal to Q over V. Q is the charge, the measure of charge in coulombs. V is volts. So again, the name of the capacitor is the capacity to store charge for every unit of voltage that is applied. So one farad is basically 1 coulomb of charge for every 1 volt. Okay, C is equal to QV. From there, we get Q is equal to CV. That's the standard equation that we will use to derive the current equation for the capacitor. The units for capacitors named after, we stated this last class. Anybody? Hemingway? That did put a chuckle on my face. Michael Faraday. Farads. So just 3 small examples. I'd like to show how the capacitance value can change depending on the amount of charge that's being stored and the amount of voltage that is being applied. So we take our standard equation, Q is equal to C is equal to Q over V. And we can see in example A, a charge of 6 coulombs is being stored in 2 parallel plates. The applied voltage is 2 volts. So the capacitance value is 3 farads, Q divided by VC. Again, this is just for informational purposes. And the second one, same voltage applied, but now if you wish to store a larger amount of charge, you need a larger amount of capacitance, right? Capacity has to be more. In general terms, if you want to store something more, you need to have more capacity. So capacitance now is 6 farads if you wish to store 12 coulombs for the same amount of applied voltage. And you can see if you increase the voltage capacity, meaning depending on the physical construction of the capacitor, the materials should be able to handle that voltage. Now the amount of capacitance required is reduced. It's only 1.5. Okay, 1.5. So 12 coulombs of charge for B and for C, but in B, you have 2 volts that is applied. In C, it's 8 volts. So the amount of capacitance required is small. And the reason it's important is because the physical dimensions of the capacitor will determine what the capacitor value is. Yes. No, it doesn't matter. It's a physical quantity, physical device, so it doesn't have any. There are certain cases where you actually have negative values for resistance and for capacitance, like we're talking about completely different theories. Okay, Physical construction of the capacitor, similar to the inductor, depends on the dimensions of the parallel plates. It is epsilon A over D, where epsilon is given by epsilon 0 times epsilon R. Remember, for inductor, it was mu, the permeability. Here, it is the permittivity. Okay, permittivity. Epsilon 0 is a constant, 8.85 in 10 raised to minus 12. Mu 0 was indeed 4 pi into 10 raised to minus 7. And then epsilon R, like mu R, is a material property. So it depends on the material that you're using for the insulation purposes. Okay, so the insulator material property gives you the value of epsilon R. A is the area of the plate in square meters. Everything is metric, so in meter square. And D is the distance between the two plates. So D is right here. Okay, that's D. Then cross-sectional area is of the plate. So now, this begs the question. Well, let me take it one step back. In an inductor, we said, right, you have a straight current carrying conductor, it has a magnetic field. But for inductance to be, to be measured or to have like a stronger magnetic field, we wind it up in a spiral coil, right? That establishes the magnetic flux lines. So if you have a long conductor, is there any inductance in the straight line or, otherwise outside of the spiral? There might be, but it's going to be very, 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 very small, right? It would not affect the actual spiral coil. So when we actually measure the inductance for the spiral coil, we start at the beginning of the first loop and the length ends at the end of the last loop, right? That's how you measure the inductance. So when it comes to capacitor, the definition of the capacitor is two parallel conducting plates separated by an insulating material. What if they are not of the same size? Here, we state the mathematical equation is the cross-sectional area of the plate. But what if the plates are not the same size? Think on that. So that's a good point. So the point being made is we would take the dimensions of the smaller plate because the smaller plate would be dictating the maximum charge that it can do, that it can store, which is a very valid point, but not quite the entire answer. What is the key term? One plate is their capacitance. Two plates is their capacitance. So if they are not of the same dimensions, there will be some areas we only have one plate. There's no capacitance. So where is the capacitance? Think on that. Anyone? Anyone online? You all are overthinking this. There is capacitance. It's only in the area where two plates are present. Not necessarily. There could be a capacitance like this and a plate like this. Could be different dimensions, different areas. Doesn't have to be the dimension of a smaller plate. Yes, the overlap. Picture is worth 1,000 words. That's always I tell my students, always draw it out. Always draw it out as many times as you need until it starts to make sense. So as soon as I drew this out, I think a light bulb went off for all of you. You could have a small plate like this, and you could have like a really big plate like this. The capacitance needs two parallel plates. The phenomenon of capacitance needs two conducting plates. So the portion of the overlap is where you would see capacitance. So when it says cross-sectional area, always keep that in mind. That was the point. Okay, Q is equal to CV. Q is charge. Current is the rate of flow of charge. So if we take dq over dt, we get current I. From current I, we can write the equation C dV over dt. So we have the current IV equation for a capacitor. Similar to resistors and inductors, it is a passive element and it follows the passive sign convention. Okay, so I of t is C dV over dt. We already did this slide. And then similar to the inductor, if you wish to find the voltage given the capacitor current, you simply integrate both sides and you get integral of the current gives you the voltage for the capacitor. And I will talk about the small last portion when we get to the example. Okay, so don't worry about the derivation. Don't worry about how we actually find it. Simple terms. I is C dV over dt, meaning the capacitor current is the product of the capacitance times the derivative of the voltage. The voltage is integral of the current. And then standard equations. P power is the product of voltage and current. And so we get CV dV over dt. And then energy is half CV square. So inductor energy was half Li square. This is half CV square. Yes. Yes. And here I've chosen these subscripts just to show you that you can come across different notations when you read different books or different authors, right? In inductor, we just had P equals VI. Here we have PC of T. It's the exact same thing. Okay, power is a function of time, or capacitor power is a function of time. Okay, let's look at 4 examples. All 4 examples basically apply equally to inductors and capacitors, right? All equations are the same. So if you go to the last slide, actually not quite the last, page 27, there is a summary slide that lists all the equations and you can compare them side by side. And you can see they have a very similar structure, right? Voltage for inductor is L di over dt. Current for capacitor is C dV over dt. For the inductor voltage and capacitor current, you simply integrate. So all the examples that you see here apply equally to capacitors and inductors. In the first example, now from this point on, the 4 solved examples, they have less to do with circuit analysis and more to do with simple math. Okay, it's just math. So at this point, you should know what equations are related to the inductors and capacitors and how you should apply them. That's all that matters. Okay, so don't try to, you can try and attain a higher level of understanding, but while you're trying to solve these problems, it's just math. Okay, so in the first one, we are asked if capacitor C has a value of 5 microfarads, find the current if the applied voltage for the capacitor is given by this mathematical expression, right? So in example 1, what do we have? We are given C, we are given V, we are asked to find the current. So as soon as you see this problem statement, think back. What is the equation for the capacitor current? I equals C dV over dt, derivative of the voltage. Do we need to do anything except math? No, there is no other circuit analysis to be performed. There's no circuit diagram. We are not analyzing for anything else beyond doing a simple math operation to find the capacitor current. So I is C dV over dt. Capacitor voltage is given to us as 5 microfarads, 5 into 10 raised to minus 6. And the expression 10 cos of 6,000 T. So before I tell you the answer, go ahead and solve this, and then let's see if our answers match up. What do you have? What is the derivative of cos x? Minus sine x, right? One of the first trigonometric identities that we ever learned. Sine x and cos x. Minus sine x. In this case, we have a cos of bx. So we have a constant in front. We use the continuity rule, bring it outside. And then we have the constant in front of the time also. And so this becomes, we'll take the minus outside. Anybody solve it yet? What do you get? That is absolutely correct. So as I was saying, cos x is minus sine x. We took the minus outside. We have the constant, and then 6,000. So 6,000 comes here, and then this becomes sine 10 sine 6,000 T. You solve that, and you obtain minus 0.3 sine of 6,000 T. And this is, of course, amps. Do not forget the amps. There is a time variable in there, right? It's a function of time. So all the answers that we will receive will have the variable t in there. This allows us to find the voltage or the current for that quantity if you plug in any value of time. Right? In the olden days, we didn't have computers, so we used to plot this manually. You would plug in t is equal to 0.1, 0.2, 0.3, 0.4, calculate the function, and then plot out the graph. Now you can take any software and create a file in Excel or any statistical spreadsheet, not statistical, any spreadsheet, and you can type in the equation. You can plot this on any online solver in your calculators, anywhere, right? But the basic principle is that it's a function of time. Okay, let's see. How much time do I have? 9:33. Should be enough. All right, example 2. If C is 2 microfarads, determine the voltage. Oh, coming back to that earlier point. This example 1 could be applied to inductor. So if it's an inductor, the question could be, L is 5 millihenry perhaps, and then I of t would be given to you. I of t would be given, and then V, voltage for the inductor, would be asked. And the procedure would be the same. Again, simple math, right? You apply the equation where voltage for the inductor is L di over dt. Does that make sense to everyone? Right? And so that's why I said all of these examples apply equally to an inductor and a capacitor. And we are looking at both. Okay? We're looking at both. Given the voltage, you find the current, and given the current, you find the voltage. Okay, now we have capacitor of 2 microfarads. I of t is given, and we are asked to find the voltage V of t. So this time we use the other equation. Okay. V of t is 1 over c integral 0 to t or t0 to t. Either ways, it's fine. I of dt. There is an extra term at the end, which is called V at 0 or V at t0. That represents the initial stored energy in that capacitor. Right now, we are not given any initially stored energy, so it's simply 0. So the value for this term is 0. It refers to the initial stored energy. And we will look at it in examples 3 and 4. Okay, so we plug in the values. Capacitor value is 2 microfarads, so we get 1 over 2 into 10 raised to minus 6. Integrate this between 0 to t. Now, the limits of the integral, we plug in t because the final answer we want is also or should also be a variable of time. Okay, so the variable is t and the limit of the integral is also t. There is no fixed value right now. Our job is to determine an expression that will be as a function of time. So I of t, what was I of t? 6 into e raised to minus 3000 t. Excuse me. Dt. Solve that and you'll have your answer. There's one more thing. Pay attention to detail. Yes. Absolutely. The current's in milliamps. So if you don't pay attention to detail, if you don't look at that M, your answer is going to be incorrect. Yes. You can, but it's better to actually just take it 10 raised to minus 3. So, what was I saying? dt, okay, 10 raised to minus 3 milliamps. And we solve this, we got 1 over 2 raised to 2 into 10 raised to minus 6. 3000 t, so minus 3000 t comes outside. 10 raised to minus 3 comes outside, so we get minus 3000, let's see. And 2 into 10 raised to minus 6 gives us 2 into 10 raised to 6, 1 over 2, half divided by, that should give me 3000 into e raised to minus 3000 t. And then the limits of the integral will be 0 to t. When we plug that in, we get minus of e raised to minus 3000 t and e raised to 0 minus of minus e raised to 0, 1. So you get minus 3000 t or minus e raised to minus 3000 t minus of minus 1. This is after plugging in the limits of the integral. So you get positive 1 minus e raised to minus 3000 t. And the answer for this should be in volts. The reason I don't like to ignore the milliamps is at the end, sometimes it might cause error in calculation. So therefore, voltage V of t . All right, questions? As I said, nothing about circuit analysis. It's simple equations and then simple solving, math solving. Okay, 9:40, 20 minutes left, and I want to get through the last two examples. So let's get going on those. All right, how many of you have heard of this technique, piecewise linear analysis, in your own engineering fields? Perhaps, maybe not. So it's a technique where what you do is you're analyzing a system or a long period of time. You wish to describe that system mathematically, but there is no way to do so. So you break it up into individual pieces, okay? And then you can describe each piece by itself. So let's say we have a voltage like this that is being applied to a capacitor, right? There is no mathematical equation given to us, and there is no way to describe this function. There's no way to describe this waveform. So what we do is we break this up into individual pieces, and each piece has a linear relationship with time. So this technique is also known as linear piecewise analysis, okay? So if I break up this input quantity between 0 to 6 and 6 to 8, each piece is a straight line. It's a linear piece, and hence linear piecewise analysis. Okay, so example 3, voltage V of t is given graphically. Capacitor C is given. We are asked to find current I of t. And you will see how easy this could be. So what I'm going to do here is, let's see. All right. First, I'm going to break up time into two parts. T1 has a value of t between 0 and 6 milliseconds. And T2 is 6 milliseconds and 8 milliseconds. And what I will use is the slope line intercept method to describe the slope of that line. It serves two purposes. One, I can mathematically describe the line. And second, what is this? M, slope, all right? We are given the voltage. If you take one piece of that voltage, describe it as a line, and x-axis is time. So if you take the slope of the line, that automatically gives us the value for dV over dt. So mathematically speaking, this is a very simple multiplication problem. That's it. Y is equal to mx plus b. Y, of course, is voltage. X is time. M gives you dV over dt. And then B, of course, is the y-intercept. Different books, different instructors, different people like to use different variations of this equation, but it's hard. It's the same standard equation for a line, for a straight line. Slope of the line can be given by any two coordinates, right? Y2 minus y1 or x2 minus x1. So we take two endpoints. I typically like to take the two endpoints of the line. And so for time period 1, I can write M1 is 24 volts minus 0 divided by 6 minus 0 milliseconds. That gives me what does it give me? 24.64. And then you simply find the current I. And 10 raised to minus 3. 4,000 volts per second. So for T1, my current I1 is simply C dV over dt. Or C times M1. Therefore, I1 is 5 into 10 raised to minus 6 times 4,000. One is 20 milliamps. 5 into 4 is 20, 20,000. 20,000 is 10 raised to 3, 10 raised to minus, yes, 20 milliamps. Yep. And if you look at it, there is no variable t. It has a constant value. So means going from 0 to 6 milliseconds, the current I has a straight line value of 20 milliamps, which, as you can see in the resulting plot. For time period T2, M2, and again, I'm going to take the two endpoints. So now I have 0 minus 24 divided by 8 minus 6 milliamps, which gives me minus 12 volts per millisecond. I2 is C times M2, which would simply be 5 into 10 raised to minus 6 into minus 12 volts per millisecond. And so, because this is 12 volts per millisecond, I have to take milli into account, and I get minus 60 milliamps, which is noted right here. Again, let's take a pause. You think through the process. You take each individual piece, describe it in terms of the slope line intercept method, straight line equation, and simply do a multiplication. Any questions? Yes. Negative 60 milliamps. No. No. It's not the rate of change of current. It's just a value of the current between time 6 and 8. It's not or. Yeah. Okay, example 4. We are given the current and now we are asked to find the voltage. And now I will talk about the stored energy initially, because if you remember last class, the year before that, in the time before that, I explained we have a system that is being analyzed for like 20 period of 24 hours, let's say, long period of time. And then we take a small piece, meaning like a minute between 59th and the 60th minute. Then we begin our analysis at the 59th minute and we end it at 60. Right? So we're analyzing for a small piece of time. Then we begin at 60 and analyze till 61. Doesn't matter where we begin our analysis in the middle, but there could be stored energy in that component from the previous time period. So if we analyze at 59 minute, there might be some stored energy before 59 minutes had gone by, right? And so when we break up this expression right here, there will be some stored energy in that capacitor for that second time period. That's the first time period. The other one's the second time period. So for the second time period, we can see there will be some stored energy from the first time period. And we have to add that stored energy into that capacitor when we do our voltage calculations. That was represented by the quantity V of T0 or V of 0. And the 0 in this case simply means the time at which you begin your analysis. So if we break this up into two parts, T1, the analysis begins at 0 and ends at 2 milliseconds. For time period T2, the analysis begins at 2 milliseconds. So T0 for T2 is 2 milliseconds. It's not 0. And this was the point I was making earlier. T0 is the beginning point of your analysis. It could have any value. So every time period, every piece will have T0. T0 for the first time period is 0 milliseconds. T0 for the second time period is 2 milliseconds. If we describe, excuse me, if we describe the slope of this first line, actually, let's look at the second one first. Second one is far easier. The second time period, if I extrapolate this, it's not quite as evident, but I'll tell you this is -8. And this here is 16. Okay, 16 microamps and 8 milliseconds. Sorry, -8. So there is no slope. The value is constant. And so we can simply write I of t has a value of -8 microamps for the second time period. Beyond 4 milliseconds, value is 0. So we don't have to worry about that. For the first one, I'm going to write the expression y equals mx plus b. B, of course, is 0 in this case. Slope of the line, m, would be 16 minus 0 microamps divided by 2 minus 0 milliseconds. You solve this and you get an answer of 8 milliamps per second, or 8 into 10 raised to minus 3 amps per second. So my expression for the first time period is I is 8 into 10 raised to minus 3 t. That describes the value of current I in mathematical terms. We have 6 minutes left. If you have to leave, you can leave. I will continue until I finish solving the problem. Also online, there are 2 more examples that you can look at. Okay, so there are 2 more examples on piecewise linear analysis, downloaded from the slides page that is on the website. All right, so I'm going to continue. For the first time period, I have to integrate from T0 to T. The end limit of the integration will always be T, because we want to derive the expression as a function of time. So the final value should always be T. T0 for the first time period is 0 milliseconds. Voltage can simply be given by integral of T Let's see. I should be doing it there. T1 is T0 to T. T0 is 0 milliseconds. X squared over T. Wait, hold on. This right here is equal to 0 volts, the initial stored energy, because there is no initial stored energy on there. So V is 1 over C integral T0 to T I, and I'm going to change the variable to X to avoid any confusion. Okay, simply changing it. So it was I of t dot dt. I'm simply changing it to ix dot dx. All right, capacitor C. What was the value of the capacitor? 4 microfarads. So we have 4 microfarads. And then we also have the slope, current, that is 8 into 10 raised to minus 3t. So I'm going to bring that outside. Constant divided by 4 into 10 raised to minus 6. And now this simply becomes x squared over 2. Limits of the integral is 0 to t. You plug in the value and you obtain voltage as 10 cube times t squared. This value of the voltage is only valid for the first time period. Okay, not for the second one. Only for the first time period. Okay, 3 minutes left. So now we go to the second time period. But when we get to the second time period, meaning when we get to here, 2 milliseconds, the capacitor has stored energy from the first time period. So what is that energy? What is the value of that stored voltage? We can obtain that by plugging in stored energy for T2. We find voltage V when the value of T is equal to 2 milliseconds by plugging in value of T as 2 in the equation above. So it becomes 10 cube times T square. T is 2 milliseconds square. And you solve that and you obtain the answer as 4 millivolts. So 4 millivolts is the initial stored energy for the second time period. It is the ending energy or the stored voltage at the end of the first time period. But for the second time period, it is the initial stored energy. Make sense? We are going a little fast, so you might have to take time to sit back and think through this after class. Okay, as I said, there's about a minute left. So if you need to leave, you can leave. The second time period is straightforward because it's a constant, right? Minus 8 microamps. So we're simply integrating a constant. When we integrate a constant, it's simply x dx. All right, value here for T0 is 2 milliseconds. I'm beginning my analysis at time 2 milliseconds. V0 for T2 is the voltage, actual voltage at T equals 2 milliseconds. So voltage for capacitor is 8 microamps. Constant, so comes outside, divided by 4 microfarads. Integral T0 to T of simply dx. Integration simply gives you t. You plug in the value or the limits of the integral in there. And you obtain this expression, minus 2t plus 8 into 10 raised to minus 3 volts. This time, the value is not constant. It is a function of time because you have the variable t in there. And we can plot this with any tool that we have at our disposal. Again, as I said, we used to manually plot it, put in value of t as 1, 2, 3, 4, 5, 6, 7, 8. Find a graphical plot. Today, you can simply plug it into a calculator or any online solver, and you would obtain an expression that looks like this. Okay. So it's simply linear, right? Because it's 2t. So it's a linear straight line for the second time period. First one was square. So if you remember, 10 cubed into 2 raised to minus, sorry, not that. 10 cubed into t square. Right? 10 cubed into t square. And so when you plot that, you obtain this for t1. So this is for t1. This is for t2. And you can manually, sorry, not manually. You can manually plot it if you want, but again, plot it on any online solver, plot it in your calculators if they're capable, or MATLAB. It won't take more than a few minutes to do so. All right, we rushed through this, but I think this is, yeah, that's the last slide, which I already went over. So that's the end of chapter 3. On Friday, we'll look at chapter 4, which is transients, the charging and discharging phase. And well, I'll be in my office later this afternoon if you want to come by with any questions. Otherwise, I'll bid you all a good day, and I'll see you all on Friday.